We are going to cover several interrelated topics today. So we're going to first start talking about electrical equivalence. I will then introduce the concept of practical voltage and current sources. That's not how you spell practical. We will lump those two things together to discuss source transformation. And we will tie everything together by talking about the maximum power transfer theorem. So we got lots of smaller topics today that are all kind of interrelated. So let's start by introducing a definition for electrical equivalence. This is actually something that we've been dealing with for quite some time in this class. It's how we're able to do all of our circuit simplification, combining sources together to make an equivalent voltage source or current source, combining resistors together to make equivalent resistances. We're just going to more formally define things here. So two networks or circuits are electrically equivalent if both networks have the same electrical characteristics. So let's say, just for the sake of argument here, that we have some voltage source Vs connected to a network that contains two resistors in series. Let's call it R1 and let's call it R2. The electrical characteristics of our resistor network in question here are going to be the voltage drop across the terminals of the network, which I'm going to call VL, and the current flowing into the terminals of the network, which I'm going to call IL. So an electrically equivalent network would be something like this, where we have that same voltage source connected to an equivalent network containing a resistance of Req is equal to R1 times R2 over R1 plus R2. And we can say that they're electrically equivalent because we will observe the exact same load voltage VL and load current IL flowing through the network. So any case, this is just a very simple example that we've already seen, but any case where the electrical characteristics of the network on the left are identical to the electrical characteristics of the network on the right means that we have an electrically equivalent network. So oh, you're right. That is a mistake there. Thank you for that. R1 plus R2. Total brain fart there. 100% correct. It should be the series equivalent resistance, not the parallel equivalent resistance, or that doesn't work. Thank you for that. Can't believe I made that simple of a mistake, but yeah. All right, or obvious of a mistake, I guess would be a better word. So in a little bit, I am going to show you guys that the following two networks are electrically equivalent. Before I detail the conditions in which these networks are electrically equivalent, I want to talk about what they are really quick. So on the left-hand side here, we have what I'm going to call a practical voltage source. And on the right-hand side over here, we have a practical current source. So let me explain what I mean by this term practical. So if we have an ideal voltage source, like so, what is the maximum amount of current that this voltage source could drive? Anybody have any thoughts? Infinite, right? Can a real voltage source drive an infinite amount of current? Absolutely not. Okay. So for a practical voltage source, let me just put here I max is equal to infinity. For a practical voltage source, the amount of current that can be driven by that source depends on its internal source resistance, which we represent simply as a resistor RS in series with an ideal voltage source. So this practical voltage source up top represents the electrical equivalent circuit model of things like batteries and power supplies and all of that kind of good stuff, where the amount of current that can leave the source is restricted to some finite value, right? Typically speaking, the internal resistance of a voltage source like a battery or things like that is usually on the order of milliohms, very, very small. And the smaller it gets, the more it behaves like an ideal voltage source. So now let's talk about an ideal current source. What's the maximum voltage? Infinity. Right. So we can actually see that for this particular circuit, right? If we viewed this circuit that I have drawn here, and I'm calling it a circuit, even though it's simply a current source, as a current source IS in parallel with some resistance R that is infinitely large, like an air gap. And we figured out what this voltage is. I times R would give us V is equal to infinity, right? So if I ever draw an ideal current source open circuited, the voltage drop over it has to be infinity because it has to be carrying that amount of current and driving that amount of current around a circuit, right? We've got a similar thing over here, right? So if I connected this guy to a short circuit with a resistance of R is equal to 0, we would see that infinite current would have to flow in order for the circuit to quote unquote work. But we can obviously short circuit the terminals of a battery and it'll spark and get really hot, but it's not going to drive an infinite amount of current. You know, a AA battery can probably drive somewhere in the ballpark of 5 to 10 amps of current for a few seconds before it completely and utterly discharges itself. But that's nowhere near infinite, right? So we use these practical sources to represent sources in physical systems, okay? And for, like I said a moment ago, for a practical voltage source, as RS gets closer and closer to 0, the practical voltage source acts more and more like an ideal voltage source. In a practical current source, when RS gets closer and closer to infinity, it behaves more and more like an ideal voltage source. Okay. So we've talked about what these practical voltage and practical current sources are, how we're going to use them in circuits. Now, let's figure out under what conditions they are electrically equivalent. Okay. So let's say that I have a practical voltage source connected to some load resistance RL. So that we measure some voltage VL across the load resistance and some current RL flowing through the load resistance. And over here on the right-hand side, I'm going to have a similar circuit. I have a practical current source, IS, in parallel with some internal resistance, RS. And across the terminals of the practical current source, I place an identical load resistor, RL. And measure both a load voltage and a load current. Okay. So if the voltage drop across my load resistance and the current flowing through my load resistance are the same, the load resistance can't tell the difference as to whether it's connected to a practical voltage source or a practical current source. So we need to figure out what are the conditions that will generate the same electrical characteristics on both sides here, okay? So we need VL to be the same on both sides, and we need IL to be the same on both sides. So let's look at VL. So on the left-hand side here, we could say that VL is going to be equal to VS times RL over RS plus RL, just using voltage division. On the right-hand side here, using Ohm's law, we could say that VL is going to be equal to IS times RS times RL over RS plus RL. So under what conditions are these two quantities equal? Let me draw this in a little bit different way. When VS is equal to IS times RS, absolutely right. Okay, so these are electrically equivalent. when Vs is equal to Is times Rs. So we've got the voltages figured out. Let's just check the currents for the sake of argument here. So on the left-hand side, our current IL is going to be Vs over Rs plus RL. On the right-hand side here, our current IL is going to be Is times 1 over RL divided by 1 over Rs plus 1 over RL. Let me give myself a little bit more room here. So it isn't super obvious in this form. So what I'm going to do is I'm going to multiply this 1 over Rs times RL over RL. And I'm going to multiply this 1 over RL times Rs over Rs. And so that's going to give me Is times 1 over RL. And then we're going to have Rs plus RL over Rs times RL. So that's going to look like Is over RL times Rs times RL over Rs plus RL. And the RLs cancel each other out. What are our conditions for the currents to be equal? The exact same thing, right? So if my source voltage is equal to my source current times my internal resistance, or any permutation thereof, right? Then my practical voltage source and my practical current source are electrically equivalent. And I can effectively go back and forth between those two forms, since they are electrically equivalent, to aid in circuit analysis. So let's look at a circuit here. Here we go. So this is a big, ugly looking circuit. And let's say, for the sake of simplicity, that we were trying to solve for the quantity Vx in this circuit. Are there any resistor combinations that we could make? Nope. There are no resistors that are connected in series. There are no resistors that are connected in parallel, right? Are there any source combinations that we could make? Nope. None of our current sources are in parallel with any of our other current sources. How many nodes does this circuit have? So I see one at the top left, one here. So it's 2, 3, 4, 5. 5 nodes. How many meshes? Also 5 meshes. So this is a pretty gnarly and ugly looking circuit. Within the next 10 minutes, we're going to boil this down to a circuit that we could have analyzed in the second day of class. And we're going to do that by using source transformations, okay? So anywhere that I see a current source in parallel with a resistor, or anywhere that I see a voltage source in series with a resistor, I can replace them with an electrically equivalent practical source that could make my analysis easier, right? So I would argue that I have 3 practical sources in this circuit right now because I have 3 current sources that are in parallel with resistors, okay? Does not matter whether or not it is a independent current source or a dependent current source. If it is a current source in parallel with a resistor, I can treat it as if it were a practical current source. So let's start by looking at this practical current source here on the left. So what I'm going to do, and this is just to help get you guys familiar with things, is I'm going to draw a pair of terminals here. Okay. So if I have a 5 amp source in parallel with a 3 ohm resistor, I can use source transformation to give me a voltage source in series with a 3 ohm resistor, where the value of that voltage source is simply going to be Vs, or excuse me, is equal to Is times Rs, right? So 5 amps times 3 ohms is just 15 volts. These 2 sources are electrically equivalent. I want to point something out here, just the rules for source transformation real quick. The value of the resistance cannot change. So if it was 3 amps in parallel with a current source, it needs to be, excuse me, 3 ohms in parallel with a current source. It needs to be 3 ohms in series with a voltage source. The positive polarity terminal of the voltage source should be on the same side as the head of the arrow on the current source, right? So if we had an arrow direction down, the positive polarity terminal of the voltage source would be down. If we had an arrow pointed to the right, the positive polarity terminal of the voltage source would be on the right, etc. So what I'm going to do now is I'm going to disconnect this practical current source by erasing it entirely and replace at the terminals with my electrically equivalent practical voltage source. So what did that do? It did 2 things here. It completely eliminated a mesh because now there are only 4 when there were 5 a moment ago. And it also happened to put that 3 ohm resistor in series with that 4 ohm resistor so that I could do a resistor combination. So I've actually introduced a node by doing this, but I've made it to where I can do a resistor combination to eliminate that node. So it's 3 in series with 4, 7. What can I do now? So I could transform the 1 amp and the 9 ohm. Absolutely, we can do that. Let's throw some terminals over here. So here is a terminal and here is a terminal. So when I have a 9 ohm resistor in parallel with a 1 amp source, what is the electrical equivalent practical voltage source? 9 volts in series with 9 ohms. Actually, let me put the terminals on the left-hand side. Does it matter what order I put the voltage source and resistor in? No, when they're in series, not at all. I'm putting them in this particular order just because that's aesthetically what we're used to, but it would not matter one bit if I put the 9 volt source on this top part of the branch and the 9 ohm resistor on the right hand side of it. Would not change the electrical characteristics at all. Okay. So I'm going to delete or disconnect my practical current source and replace it at the terminals with a practical voltage source. What else can I do? So I'm not going to add the 2 and the 9 together because our voltage Vx that we're trying to find is defined as the voltage drop over that 2 ohm resistor. And as soon as I get rid of that 2 ohm resistor, the voltage drop Vx is no longer a thing. So because that's controlling a dependent source, I need to leave that one alone. Okay. I'm sorry, what? Absolutely. It's a practical source. So sure. So we can do that one. Okay. So I'm going to put a terminal here and a terminal here. So I have make sure I'm getting the direction right there. Yep. Oops. Screen moved on me. So I'm going to have something in series with a 17 ohm resistor. That something is going to be a practical, or excuse me, a dependent voltage source because I had a dependent current source. Since my arrow is directed to the right, my positive polarity terminal is going to be on the right. I'm simply going to multiply 3 amps per volt. That's the units here, right? Because this is a times 17 ohms, which is 17 volts per amp. And so I'm going to get 3 times 17 is 51 Vx. Even the units work when I do this, right? So I'm going to disconnect this guy here. All right, what can I do now? Positive polarity terminal should be on the other side, actually. Yeah. Sorry about that. I drew it wrong. Minus plus like that. Yeah. Thank you for that. We could add the 17 and the 9 together for sure. All right, so 17 plus 9 is 26. Throw that over here. We could, but it's going to be a little bit wonky, like it would just be 9 minus 51 VX or something like that. Probably best to just leave it as it is. There is something that we can do though here. We could, but we didn't know mesh on the second day of class. Or the third day of class or whatever it was. What if we did a practical, what if we did a source transformation on the practical voltage source on the left-hand side here? 15 in series with 7 is going to look like some sort of current source, right? So this would be 15 over 7. That is not a 7. In parallel with 7. Scroll too far. Which places my two 7 ohm resistors in parallel. So I can combine them into 7 over 2 ohm resistor. And now I'm going to convert that practical current source on the left back into a practical voltage source. So that would be 15 over 7 times 7 over 2 is going to be 15 over 2 volts. In series with a 3.5 ohm resistor. 3.5 plus 26 looks like 29.5. And let's see, 9 minus 7.5 looks like 1.5. And boom, we have a trivial single loop circuit that we could have analyzed on the second or third day of class just by using, granted, a lot of source transformations. Okay. So this can be, Sophie, did you have a question? All righty. So let's back things up here a little bit. So this was 26. We had a 7 ohm resistor here. 7 ohm resistor here. And a 15 volt source here, right? So I converted my 15 volts in series with 7 ohms into 15 over 7 amps in parallel with 7 ohms, right? I then observed that my 7 ohm resistor was in parallel with another 7 ohm resistor, giving me 7/2 of an ohm of resistance. Then I converted that practical current source on the left into a practical voltage source. So that would be 15 over 7 times 7 over 2 gives me 15 over 2. In series with 7 over 2. I can then observe that my 7 over 2 ohm resistor is in series with my 26 ohm resistor. So I can add them together, giving me 29.5. And I can also see that sorry, this should have been a 9-volt thing over here the whole time. My 9-volt source is in series with my 15 over 2 volt source, but they are of opposite polarity, so I'm going to take the difference of them. So 9 minus 7.5 gives me 1.5. And I turn that guy off.
You just subtract the smaller one from the bigger one.
That's what I did, yeah. Because I didn't want a negative number, because I don't like them. And then now I have a simple single loop circuit that we could solve for Vx pretty easily, right? So if we wrote a KVL equation, let's just call this current I, we'd have negative 1.5 volts plus 31.5 I minus Vx plus 51 Vx is going to look like plus 50 Vx is equal to 0. Well, Vx is simply negative 2I. Or we could say that I is equal to Vx over negative 2. Substituting that in up here, we have 31.5 times negative Vx over 2 plus 50 Vx is equal to 1.5 volts. And let's throw this in my numerical solver since my brain doesn't seem to be working very well this morning and I don't want to make another simple mistake. 31.5 times negative x over 2 plus 50x is equal to 1.5. Solve for x. $43.796 millivolts.
So you have the get 52
Because I had a 15-volt source, so when I had the 15-volt source, or excuse me, in series with a 7 ohm resistor, I can convert it into a practical current source, which is going to be, so if we know that Vs is equal to Is times Rs, then Is is simply Vs over Rs. So when the 7 ohm resistor and the 7 ohm resistor are in parallel, they look like 3.5, right? Or 7 over 2. So I had a 15 over 7 amp source in parallel with 7/2, which looks like 15/2 volts in series with 7/2. And then from there, since that 7/2 is now in series with the 26, I can add them together. And since that 15/2 volts is in series with the 9-volt source, I can combine those as well. Mhm. All right, so this was a bit, yes. You're right. No, that is absolutely a mistake. Yeah, so it should have been 29.5 I plus 50 VX. Thank you. Brain isn't working today. I did, but I added the 2 and then I also subtracted a VX, and it can't be both. It should only be one or the other. Right. So all right. Let's take another crack at this whole thing because there are so many questions. All right. So what I'm doing here, I apologize for my brain not working this morning. I'm writing a KVL equation starting here. So I see the negative polarity terminal of my 1.5 volt source. So I have negative 1.5 volts. Now I need the voltage drop across my 29.5 ohm resistor. So that's going to look like plus 29.5 ohms times I. Then I see a minus Vx. Then I see plus 51 Vx. And I set this equal to 0. Okay. I can say that I is equal to negative Vx over 2 ohms, substituting that in here. So I'm going to have 29.5 ohms times negative Vx over 2 ohms plus 50 Vx is equal to 1.5 volts. And I find that Vx is 42.553 millivolts. I apologize, Phil, for adding, or no, it wasn't Phil that pointed it out. It was Elizabeth, I'm sorry, that pointed out that I was effectively counting the voltage drop across the 2 ohm resistor twice. That was very much incorrect. So thank you for pointing that out. Yes. You could, and you would have negative 51 Vx plus 29.5 ohms. Are you assuming I is flowing in the same direction or the opposite direction? It does not matter. I just arbitrarily chose the current leaving the positive polarity terminal of my independent source, but I could have just as easily said the current was leaving the positive polarity terminal of my dependent source and wrote it the other direction. You get literally the exact same answer. Yeah. Okay. So I sincerely hope that I haven't confused you guys too terribly much for this. We're going to use it again in a moment. But I want to talk about the maximum power transfer theorem. So let's say that we have a practical voltage source connected to some load resistance RL. Here's our voltage VL. Here is our current IL, like so. VL is given by using voltage division, VS times RL over RS plus RL. And IL is given by VS over RS plus RL. The power absorbed by our load resistor is then just the product of VL and IL, which is going to be VS squared times RL over RS plus RL quantity squared. So if I were to plot the power absorbed by our load resistor as a function of load resistance. So in my y-axis, I have PL as a function of RL. And on this axis, I have RL effectively increasing from 0, where RL would be a short circuit, all the way out to effectively infinity, where RL looks like an open circuit. What I would have would be something, a curve that looks something like this. Right, where this is RL going towards infinity. There is a single value of resistance that will cause that practical voltage source to deliver the maximum amount of power that it possibly can. So our goal here is to figure out what that is. So how do we find the maximum value of a function? Take the derivative and set it equal to 0, right? So we are going to take the derivative with respect to RL of our PL equation. VS squared times RL over RS plus RL quantity squared. I'm going to call this bit up here F, this bit down here G, and I'm going to use the quotient rule, right? Where the quotient rule says the derivative of f of x over g of x is equal to the derivative of f of x times g of x plus f of x times the derivative of g of x over g of x squared, right? You guys all did that in Math 241, I think. Probably. I may have wrote it down on my Post-it note wrong. All right, so what is the derivative of VS squared times RL? times RS plus RL quantity squared. You guys say it should be a minus sign, so let's run with that. Probably should be a minus sign now that I'm looking at it. What is the derivative? Excuse me, then we're gonna have VS squared times RL. What's the derivative of RS plus RL squared? Right, so that's taking the derivative of the inside and then chain ruling it or something, right? Okay. Did I do that calculus right, or did I screw it up? What's G squared? Okay, so I want this to be equal to 0, which means the numerator needs to be equal to 0. Right? If the numerator is equal to 0, the whole fraction is equal to 0. And there's no way the denominator is ever going to be equal to 0 unless we're dealing with negative resistances anyway. So let's bring that down. Let's do some expanding things here, right? So I have VS squared times RS squared, that is plus 2 RS RL plus RL squared minus VS squared. Oh, let's see. Feel like I'm going to make a mistake here. So 2 RS times RL then I'm going to have 2 RL times RL, so that's just 2 RL squared. Let's see. 2 RL times RS is that. 2 RL times RL is that. All right. Anybody see any algebraic errors here? Genuine question because my brain does not appear to be working this morning. Elizabeth, you're looking at the screen incredulously. Where do you think I made a mistake? Okay, that's great. Okay. Everybody okay with the algebra that I'm throwing out here? Real question. I've made so many mistakes today, it would not surprise me whatsoever that I was screwing something up here. Okay. So let's figure out what here is going to cancel out, right? So there appears to be a VS squared times 2 RS RL with a positive sign from the left-hand part, and there appears to be a VS squared times 2 RS RL with a negative sign in front of it on the right-hand bit. So I believe that this bit and this bit are going to cancel each other out. Anybody have a problem with that? So VS squared. Actually, since I have VS squared on both sides of this, I could just divide both sides by VS squared to get rid of that, right? Yeah. So that's going to leave me with RS squared plus RL squared minus 2 RL squared is equal to 0. I'm going to combine So I'm going to have RS squared minus RL squared is equal to 0. And so from here, I can say that for maximum power transfer to occur, RL needs to equal RS. Coming back up to my graph. I'm just going to write in here that RL is equal to RS. So maximum power transfer occurs when our load resistance is identical to the internal source resistance of our practical voltage source. We could do a similar derivation with a practical current source and we would see the exact same results, right? Maximum power transfer is always going to occur when our load resistance is equal to our source resistance. So if we evaluate this expression under the condition that RL is equal to RS, what we will have is an equation for our maximum power, right? So that's going to be VS squared times RS over twice RS quantity squared, which is going to look like VS squared divided by 4 RS. If we had a current source representation instead of a practical voltage source representation, our maximum power would be 1/4 IS squared times RS. So these are our equations for maximum power transfer. The one on the left is for when we have things connected to a practical voltage source. The one on the right is for a practical current source. So let's tie literally everything that we've done today together and look at one last circuit. Screen is being weird. So let's say that I have a 12-volt source connected to a 3-ohm resistor, connected to a 6-ohm resistor, connected to a 7-ohm resistor, connected to some resistance RL. And I want to figure out A, what value of RL will cause the remainder of the circuit to deliver maximum power. And B, what is the maximum power that RL can absorb? So effectively, what our goal here is to reduce everything that is connected to RL down to either a practical voltage source or a practical current source. Once we have the practical voltage source or practical current source representation of the remainder of the circuit, we can see what the source resistance is. And that will give us the answer to part A. And then we will simply apply our maximum power transfer equation to get the results for part B. This is usually how I ask this type of question on the exams. And if you look at the practice test, you will see that pretty much the last question on the exam is usually something like this. Actually, we'll talk about that in a moment. I want to look at a practice test or two just to explain a couple of things here before we completely finish here. So how am I going to reduce this down into a practical voltage source or a practical current source? Sorry, I drew that poorly. That should be a 3 ohm, but you're correct. We have a practical voltage source on the left-hand side. So Elizabeth, what would I replace that practical voltage source with? Four amps in parallel with 3 ohms. I agree wholeheartedly. So here is our 3 ohm resistor. Over here, we will put our 4 amp source. Did I get the direction for the current correct? Yes. Okay. So what can I do now? So 3 ohms in parallel with 6 ohms looks like what? 2. Silas, what can I do now? All right, so it's going to be a practical voltage source. What's it going to look like? That is a 4. 8 volts in series with 2 ohms, absolutely correct. What can I do now? Add 2 and 7. So make this a 9 ohm resistor, and I'm done. Right? VS is 8 volts. RS is 9 ohms. So to answer part A, RL needs to equal to RS needs to equal to 9 ohms. What is the maximum power that can be absorbed? Pmax is going to be VS, so that's going to be 8 volts quantity squared over 4 times 9 ohms. Looks like 64 over 36 volts, which could be simplified, but I'm lazy and not going to do it. So just so we're super clear here, this is effectively the level of question that you should expect on your exam. To illustrate that, I want to go back and look through some of the practice tests real quick. 221, old tests. So let's look at this one from fall of 2019, just for the sake of argument. We'll probably take a look at another one as well. Make this smaller. So one thing that students seem to rarely figure out, go away thing. I don't know why this isn't scrolling. Your test on Thursday evening. So this is an old test that I used to give. It's 35 questions long, and this was when I used to give 3-hour tests. The dean of the College of Engineering and Science, Dr. Heegab, literally told me that I was being too mean and to make the test shorter. Okay, so they're no longer 35 questions, they are now 25 questions. So the first 10 questions on this exam are effectively short theory questions or whatever. There will only be 5 of them on your exam. Okay, so only 5 theory questions. Let me go to the next page here. So the first 10, reviewing some of those definitions and all that kind of stuff we talked about. Then we get into this thing. So I want power absorbed using generic circuit elements and all that kind of stuff. So this is very much like what we talked about on the second day of class. Then we have current and charge relationship. So that's second day of class stuff. Energy and power relationship, second day of class stuff. Resistor combinations, we're now into the third or fourth day of class. Effectively, it took you guys forever to figure out that I put stuff on the test in the exact same order that I taught it. Okay. So this question, I'm expecting you to use current division. Then we're getting into superposition. So the contribution of blah, blah, blah source to the quantity. So that's definitely a superposition problem. Here we get into using nodal and mesh. And then here we have, this one looks. Yeah, so this is, what value of RL can absorb maximum amount of power. So this is using source and voltage transformations as well as the maximum power transfer theorem. And then we get into these horrifying looking things here. I stopped putting questions like this on the exams. Yeah. I thought they were very easy points. The students tended to disagree because it was literally just write the correct equation or figure out which of these equations is correct for this thing or whatever. But I stopped putting what I call big ugly nodal and big ugly mesh problems on the exam because apparently it gives you guys panic attacks to see something that's terrifying. Not making you solve it or anything like that. So it's literally just going to be small circuits that you can use. I say easily because I'm a jackass, but small circuits that you can analyze in a reasonable amount of time. Typically speaking, I try to give 2 to 3 questions per actual circuit that you're trying to analyze, so that you're not analyzing 20 circuits, you're really analyzing 6 or 7 circuits and giving me 2 or 3 different parts. I would argue that the best way to study for any of my exams is to look at these old tests and to look at the in-class assignments, because for the most part, all of these old tests, I wrote everything. I also wrote all of the in-class assignments, and I write the overwhelming majority of the test problems. Until this year, I wrote literally all of the test problems until Dr. Swanbaum and Dr. Kronk said they wanted to participate in the test writing process. So they each have literally 2 to 3 questions per test. Everything else is me. Okay. So anyway, so I still firmly believe that studying my old tests and studying the in-class assignments and all that kind of stuff is the way to study for this exam. You should be doing your homework anyway because it's, I don't know, 2 letter grades or something ridiculous like that. So that's also good-ish practice, but really trying to figure out the kind of stuff that I like to put on the tests. It's this stuff because I put it on the tests. Okay, so 2 hours. Yeah, so you have 2 hours to take the exam. If you are a standard time student, you have 3 hours to take the exam. If you're an extended time student, standard time students, like I said, over here will be in ISB 318. Extended time students will be in ISB 222. The exam starts at 6 p.m. this Thursday, March the 30th. All right, that's enough out of me for today. So work on your in-class assignment for the next 30 minutes or so. If you have any questions, I will try to remove my head from my ass to be able to help you.